Hi, I am Sanjay Patel. In this video, we are going to discuss the nth derivative of a particular function y is equal to x plus square root of x square plus 1 whole raised to m. And we are going to use Leibnitz theorem for finding the nth derivative of this. And then later we will see that there are many other problems which can be solved with the help of the nth derivative of this function. We have done a similar thing in our previous video and discussed nth derivative of many functions using the basic function y is equal to x plus square root of x square minus 1 raised to m. Okay, so let us begin with our next problem. We have solved so far 8 problems in this topic of Leibniz theorem. Let us start with the first problem of this lecture. If y is equal to x plus square root of x square plus 1 whole raised to m, then prove that x square plus 1 times yn plus 2, okay, plus 2n plus 1 into x into yn plus 1 plus n square minus m square into yn is equal to 0. This is yn plus 2. Okay, let us solve this. Here we have the function y is equal to x plus square root of x square plus 1 whole raised to m. Okay, so taking or differentiating this with respect to x on both the sides, differentiate with respect to x, what we get is the first derivative y1. On the right hand side we have something raised to m, so its derivative is m times something raised to m minus 1. So we'll get this thing, and then again we have to find derivative of this x plus square root of x square plus 1 using the chain rule. So we'll write that thing here in the square bracket. Derivative of x is 1 plus derivative of square root of x square plus 1 is 1 upon 2 root of x square plus 1 into 2x. Okay, so this is our first derivative. Let us simplify this. Okay, so this implies we'll get y1 is equal to m into x plus square root of x square plus 1 whole raised to m minus 1 into, taking the LCM, square root of x square plus 1 here. Okay, what we get, first of all let us cancel these 2 here, and we get 1 into square root of x square plus 1, that is this, plus x. Now multiplying this by square root of x square plus 1, we get square root of x square plus 1 into y1 is equal to m times, now we have 2 terms, x plus square root of x square plus 1 raised to m minus 1, x plus square root of x square plus 1 whole raised to m minus 1 into x plus square root of x square plus 1. Okay, this I can simplify and write it as square root of x square plus 1 into y1 is equal to m times x plus square root of x square plus 1 whole raised to m. But this term is nothing but our function y. As you can see here, we have started with the function y is equal to x plus square root of x square plus 1 raised to m. So I can replace this by y, and what I get is an important step. So this implies we get square root of x square plus 1 into y1, x square plus 1 into y1 is equal to m into y. Okay, now squaring both the sides, we get x square plus 1 into y1 square is equal to m square into y square. So this is again an important step. Now, to obtain the required relation, this one, we have to first find the relation between y1 and y2, because that we already know how to think to prove such relations in nth derivative or in Leibniz theorem problems. Okay, so again we differentiate this with respect to x on both the sides. So again differentiate with respect to x. On the left hand side we have product of two functions. So first I am keeping x square plus 1 as it is. Derivative of y1 square is 2 into y1 and derivative of y1 is y2. Plus now y1 square as it is, and derivative of x square plus 1 we can write as 2x plus 0, that is 2x. On the right hand side we have m square into y square. So m square is a constant in multiplication, will remain as it is. Derivative of y square is 2y into y1. Okay. Now we can see in this equation that 2 into y1 is common in all the steps. So we can cancel this. So this 2y1 here, this 2 and y1, and 1 y1 from this and 2 will be cancelled. So what we are actually doing is we are dividing by 2 times y1. Okay, so this gives us x square plus 1 into y2 plus x into y1, and here what remains is m square into y, which I want to write in the left hand side. So it will be m square into y is equal to 0. Okay, now we have obtained relation between y1 and y2. So we'll take nth derivative in this equation. So taking nth derivative on both the sides, we get this thing, x square plus 1 into y2, its nth derivative, which we write like this, then x into y1, the product of these two functions nth derivative, minus, here we have only one function y, m square is a constant, so m square will keep as it is, and nth derivative of y is yn, and on the right hand side 0, nth derivative is 0. Okay, now for each of these square bracket there are product of two functions, so we'll use the Leibniz rule for finding the nth derivative for product of these two functions. So here among these two functions x square plus 1 and y2, this function's third derivative is 0 because it is a polynomial of degree 2, so third derivative is 0, so this we choose as v according to our simple rule, and this I will take as u. Okay, so this implies applying the Leibniz theorem for the first bracket, nc0, the first term, into nth derivative of u, that is nth derivative y2, which is yn plus 2, into the function v as it is, that is x square plus 1 as it is. Okay, and plus nc1 into 1 less than this, that is yn plus 1. The next we have to decrease by 1 into first derivative of v, that is first derivative of x square plus 1, and that is 2x plus 0, plus nc2 into 1 less than yn plus 1, that is yn, and the next derivative of 2x is only 2. Now if you go for the third step or the next step, the derivative of 2 will be 0, and then onwards all other derivatives will be 0, so no need to write other terms after this stage. Okay, this plus, again applying the Leibniz rule for finding nth derivative of product of these two functions. This is a polynomial of degree 1, so its second derivative is 0, so this I will take as v and this as u. So this implies what we get here is nc0, y1's nth derivative is yn plus 1, then x as it is, plus nc1, and the one less than this, that is yn, into first derivative of x, that is 1. Now this 1 is constant, so in the next term its derivative will be 0, so we don't write and close the bracket here. Minus the last term I am keeping as it is, minus m square into yn is equal to 0. Now let us simplify this. nc0 is 1, so yn plus 2 into x square plus 1 I will write like this, x square plus 1 times yn plus 2 plus nc1 is n and 2x, so 2x into n into yn plus 1 plus nc2, that is n into n minus 1 by 2 factorial into yn into 2. So these two will be cancelled. Plus, now for this bracket again, nc0 is 1 into x, so it is x into yn plus 1. And here nc1, that is n into yn, so plus n into yn, and last step is as it is, minus m square into yn is equal to 0. Okay. Now let us simplify this step. So here, if you simplify this by collecting similar terms, first term is single, so that will keep as it is, yn plus 2th term, plus you observe that there are two terms containing yn plus 1. One is this and other is this one, and from both the terms we have yn plus 1 and x common, so what remains is 2n plus 1 into x into yn plus 1. Now for the remaining terms, we have yn common, 1, 2 and 3. There are 3 terms containing yn, so keeping yn outside and simplifying the remaining, n into n minus 1 gives you n square minus n, then plus n and minus m square into yn is equal to 0. Okay, so here we can cancel these two, and what we get is our required result. So we have proved that nth derivative of y is equal to x plus square root of x square plus 1 whole raised to m is given by this thing, this equation, n square minus m square into yn is equal to 0. Hence, this result is proved. Let us go to the next problem. This is problem number 10. If y raised to 1 upon m minus y raised to minus 1 upon m is equal to 2x, then prove that we'll get the same result as in this previous problem. So let us copy this. Okay, fine. So we are going to prove the same result for this new function. As I told you, there are many other problems which you can solve using the technique of the first problem of this lecture. So let us solve this. Here we have the function y raised to 1 upon m minus y raised to minus 1 upon m is equal to 2x. The function is given by this equation. Okay, and let us see what to do in this case. There are two things, y raised to 1 upon m, which appears at two places. So let us take a substitution. Let us take a substitution for y raised to 1 upon m as t. So this implies y raised to minus 1 upon m is t raised to minus 1. So it is 1 upon t. So we can write the given function as t and then minus sign, and y raised to minus 1 upon m means y raised to 1 upon m whole raised to minus 1. So I can write it as t raised to minus 1, or I can directly write 1 upon t is equal to 2x. Let us simplify this. So we'll get t square minus 1 is equal to 2xt, multiplying both the sides of this equation by t. Now taking the 2xt in the left hand side, we can write it as t square minus 2xt minus 1 is equal to 0. Okay. Now I want to make the first two terms into perfect square. So the last term is missing, and which is clearly, as you know, how to make into a perfect square. So we must add and subtract x square here. So x square minus 1 is equal to 0. Now collecting the two groups, one is this and other is this, we can rewrite this step as t minus x whole square, and taking this x square and 1 on the other side, we'll get x square plus 1. Okay. Now taking positive square root here on both the sides, what we get is t minus x is equal to square root of x square plus 1. So taking only positive square root. Okay. Now this implies we can rewrite this as t is equal to x plus square root of x square plus 1. But what is t? T was y raised to 1 upon m. So we'll get this thing, because t is equal to y raised to 1 upon m. And this implies we can write this as, by taking mth power on both the sides, we can write it as y is equal to x plus square root of x square plus 1 whole raised to m. What we have done is taking mth power on both the sides. Okay. And now this given equation or the given function here in this problem reduces to this function y is equal to x plus square root of x square plus 1 raised to m. So you can just write down the same solution. See, it is the same function as in this problem number 9. So we can prove the same result. So from now onwards, you can just write down this simply this whole solution and write it over here. So this is same as problem number 9. Okay. So let us solve the next one. Problem number 11. If x is equal to cot 2 theta and y is equal to cot raised to m theta, then prove that x square plus 1 into yn plus 2 plus 2n plus 1 times x into yn plus 1 plus n square minus m square into y is equal to 0. So again, it is the same thing as in the previous problem. Here n square minus m square. Okay, so it is the same thing. We have to prove same equation. So let us begin. So solution here, we have the function y is given in terms of parametric equations. X is equal to cot 2 theta and y is equal to cot raised to m theta. We want to find dy by dx, that is y1, d2y by dx square y2, and obtain relation between y1 and y2. You can use the derivative of parametric functions to find dy by dx and d2y by dx square. But instead of that, we'll eliminate this parameter theta and obtain direct relation between x and y, or we'll find the function y as a function of x. So this implies we can write x is equal to 1 upon tan 2 theta. We know the formula of tan 2 theta is 2 tan theta upon 1 minus tan square theta. And then taking the reciprocal, we can write this as 1 minus tan square theta upon 2 into tan theta. Okay. Here, for y is equal to cot raised to m theta, let us take 1 upon mth power on both the sides. So we can write it as y raised to 1 upon m is equal to cot theta. And let us call this as t just for simplicity. So cot theta is t, so tan theta is 1 upon t. Okay, so therefore tan theta is equal to 1 upon t. That I can substitute here. So what I will get here in this first part is x is equal to 1 minus 1 upon t square upon 2 into 1 upon t. Let us simplify this. So this gives us x is equal to, this is t square minus 1 and upon t square, and that 1t will be cancelled, so we'll get 1 upon t into 2. Simplifying further, what we get is 2xt is equal to t square minus 1, and that gives us t square minus 2xt, okay, t square minus 2xt minus 1 is equal to 0. Now to make this into a perfect square, again as usual, let us add and subtract x square, which is same as the previous problem. So plus x square minus x square, this minus 1 equal to 0. And now taking these two groups, 1 and this 2, what we can write next as the first group as a perfect square, t minus x whole square, and the second group I am writing on the right hand side. So it will get x square plus 1. This implies you will get t minus x taking the positive square root is equal to x square plus 1 square root. Now taking that x on the other side, we get t is equal to x plus square root of x square plus 1. Now what was t? So t was y raised to 1 upon m. So putting the value of t, we get y raised to 1 upon m is equal to x plus square root of x square plus 1, okay, because t is equal to y raised to 1 upon m. Now taking mth power on both the sides, we get y is equal to x plus square root of x square plus 1 whole raised to m. Okay, what we've done is we've taken mth power on both the sides. Okay, now this is same as our first problem, problem number 9. So we can just write the same solution and obtain the same result what is required in this example. That is just writing the solution of problem number 9. It is same. To find the nth derivative of this function, we get x square plus 1, this one, x square plus 1 into yn plus 2 plus 2n plus 1 in times x into yn plus 1 and so on. So I can write directly. Then this is same as the problem number 9. Okay. Now let us go to the next problem, problem number 12, and that is if x is equal to 1 by 2 times tan theta minus cot theta and y is equal to tan raised to m theta, then prove that the same thing, that is x square plus 1 into yn plus 2 plus 2n plus 1 into x into yn plus 1 plus n square minus m square into yn is equal to 0. So we'll show that this problem also we can reduce to the problem number 9. So problem number 9 is our model problem of today's lecture, and we are going to solve other problems of nth derivative using this. Okay. So let us solve this. Here we have again the function y is given in terms of parametric equations 1 upon 2 times tan theta minus cot theta, and y is equal to 10 raised to m theta. Okay. So what we can do is first of all, let us write this as y raised to 1 upon m is equal to tan theta, and let us call it t. Let us call it t. And putting the value of this tan theta here in this, we get x is equal to, let me write 2x is equal to, taking 2 on this side, tan theta is t, so t, and cot theta means 1 upon tan theta, so it is minus 1 upon t. Simplifying, what we'll get is 2x is equal to t square minus 1 upon t, and again simplifying this, we'll get t square minus 1 is equal to 2xt, taking cross multiplication. Now this is again same as that previous problem, t square minus 2xt minus 1 is equal to 0, and we have made this into a perfect square many times. So t square minus 2xt plus x square minus 1 is equal to 0, and that gives us the same thing, taking this group and this group. What we can write is t minus x whole square is equal to x square plus 1, taking these two on these sides. So this gives us t minus x is equal to square root of x square plus 1 by taking the positive square root only. And this gives t is equal to x plus square root of x square plus 1. Now putting the value of t, which is y raised to 1 upon m, again we see that in the next step this is reduced to the same function of problem number 9. So taking mth power both the sides, we will get y is equal to x plus square root of x square plus 1 whole raised to m. So now we can proceed to just add the solution of problem number 9 here. So this is same as problem number 9. Okay. Let us go to the next problem. This was problem number 12. Now we'll go to the problem number 13, the last problem of today's lecture. So problem number 13 is if y is equal to x minus square root of x square plus 1 whole raised to m, then prove that the same thing, x square plus 1 into yn plus 2 plus 2n plus 1 into x into yn plus 1 plus n square minus m square into yn is equal to 0. So that required result is same as the problem number 9. Okay. So first of all, let us consider the given function, and we'll find the second derivative of this and obtain a relation between y1 and y2. Okay. And we'll get the same type of equation as in problem number 9. So differentiating with respect to x, we get y1 is equal to m into x minus square root of x square minus 1 raised to m minus 1. X raised to n derivative is n times x raised to n minus 1. So using that into derivative of this thing, derivative of x is 1 minus derivative of square root of x square plus 1 is 1 upon 2 root of x square plus 1 into 2x. So this 2 gets cancelled, and then we'll simplify this further. So y1 is equal to m into x minus square root of x square minus 1 whole raised to m minus 1 into taking the LCM here in the square bracket as square root of x square plus 1. What I get here is square root of x square plus 1 and minus x. Okay, that is important. Now this implies I am multiplying here on both the sides by, say, square root of x square plus 1. Multiplying this equation by square root of x square plus 1, we will get square root of x square plus 1 times y1 is equal to m into x minus square root of x square plus 1. This is plus 1 everywhere. I forgot here. This is plus x square plus 1. So x square plus 1 raised to m minus 1 into, okay, and here in this second this square bracket, I want to take minus sign common, that I will write here, and what remains here will be x minus square root of x square plus 1. So this gives us square root of x square plus 1 times y1 is equal to minus m into x minus square root of x square plus 1 raised to m. This is a raised to m minus 1. This is a. So the product will be a raised to m only. And now this bracket or this term is nothing but the given function y. As you can see here, y is x minus square root of x square plus 1 whole raised to m. So putting the value y in place of that thing, what we get is square root of x square plus 1 into y1 is equal to minus m into y. Okay. Now squaring both the sides. So squaring both the sides, we get x square plus 1 into y1 square is equal to m square into y square. Okay. So this result star is same as the result in our first problem, that is problem number 9. Let me show you that. Here it is. X square plus 1 into y1 square is equal to m square y square. So after this, we can continue in the same manner and we'll get the same solution. So x square plus 1 into y1 square is equal to m square y square. We obtained in that last example. So then onwards, you can write down the same solution. So there is no change. So just I will mention there. I will mention here in this problem number 13. Let us not call this a star. Let us call it as result number 1 here. The result 1 is same as the result star of problem number 9. Okay, so you can write down the same steps after that star of problem number 9 and you will get the same result. Okay, so just use the problem number 9 here. Therefore, just write the solution of problem number 9 after, just use problem number 9. Okay, so in this lecture we have seen how to find the nth derivative and solve related problems of the function y is equal to x plus square root of x square plus 1 raised to m. In the next lecture, we are going to solve some difficult problems based on Leibniz theorem, some special problems which we can solve using Leibniz theorem. So thank you.